There is a type of star that has discovered the trick to cheat death. While our sun is violent and wasteful, burning its fuel in a frenzy that will kill it soon, red dwarfs are the absolute masters of efficiency. Unlike normal stars, they constantly mix their insides, recycling every gram of hydrogen and refusing to waste anything. Thanks to this cosmic stinginess, they can live for 10 trillion years. Today, we are going to meet these little red candles that, thanks to their infinite patience, will be the ones to watch over the corpse of the universe when all the other lights have gone out. What makes a red dwarf so special in the vast catalogue of stars in the universe? To understand this, it's first necessary to know what exactly a red dwarf is. It is a type of small and relatively cool star when compared to larger and brighter stars like the Sun. But cool compared to what? Although its surface can reach about 3,000 degrees Celsius, this is much less than the surface temperature of more massive stars. Red dwarfs are true dim beacons. They shine faintly and often go unnoticed, even when they are close to us in space. How do they differ from the rest? A red dwarf is a low-mass star, generally with less than half the mass of the Sun. They are so modest in size that if we could place one next to our Sun, the difference would be like comparing a tennis ball to a watermelon. But, although small, they are incredibly abundant. In fact, they make up the majority of stars in the Milky Way. Their light, dim and reddish is a result of their low surface temperature, giving them that characteristic color that inspires their name. Have you ever wondered why these stars live so long? The key lies in their internal workings. Red dwarfs fuse hydrogen in their core in a much slower and more efficient way than larger stars. It's as if they are cosmic energy savers. They consume their fuel with great patience, allowing them to live for hundreds of billions of years. This longevity is not only astonishing, but means that no red dwarf has yet reached the end of its life, given that the universe is too young to have witnessed the death of one. Finally, what role do they play in the universe? Despite their modest appearance, red dwarfs are essential for understanding stellar evolution and the possibility of life on other planets. Their stability, large numbers, and long life make them silent protagonists of the cosmos. If advanced civilizations ever existed in our galaxy, it is likely that many of them orbit around these small and persistent suns, which have witnessed almost the entire history of the universe without hardly changing.
If you're enjoying this journey through the universe and want to keep exploring more cosmic mysteries, don't forget to subscribe to the channel and give the video a like. Thank you for being part of this star odyssey.
Have you ever stopped to think about why we call this particular type of star a red dwarf? The term sounds simple, but it hides a whole story of astronomical observation and classification. In astronomy, names are not chosen at random. Each word reflects a key characteristic. Why dwarf? Why red? Behind these words lie centuries of discoveries and a constant attempt to describe the universe as accurately as possible. The term dwarf began to be used in the late 19th century when astronomers sought to distinguish between stars that, despite their apparent brightness, turned out to be much smaller and less luminous than other giants in the sky. The telescopes of the time revealed that not all bright stars shone equally. Some, although close, barely stood out in the sky. Thus, the distinction between giants and dwarfs was born. The word dwarf served to indicate those stars that, while sharing the same basic nature, were much more modest in size and energy. And why red? The answer lies in their characteristic color, a direct result of their surface temperature. The stars we call red dwarfs emit most of their energy at longer wavelengths, giving them that reddish hue when observed through scientific instruments. For astronomers in the early 20th century, color was a fundamental tool for classifying stars, so they combined the reference to size with the reference to color to create a clear and descriptive category. Thus, red dwarf came to designate the smallest, coolest, and longest-lived stars in the universe. The origin of the term is also linked to the evolution of knowledge about stellar physics. When it began to be understood that color indicated temperature, and that there were stars much cooler than the Sun, the need for a distinctive name became evident. It's interesting to think that, in a way, calling these stars red dwarfs is almost like nicknaming a small, efficient car Mini-Red. It's a simple nickname, but it condenses key information, size, color, and, by extension, many of their essential properties. In summary, the name red dwarf arises from the astronomer's need to describe, classify, and differentiate these stars from much larger and hotter ones. It combines visual observation with scientific understanding, and it has endured because it manages, in just 2 words, to convey the essence of one of the most abundant and fascinating types of stars in the cosmos. Who would have thought that such a simple name could hold so much history and science? Where do red dwarfs hide in the vast stage of the universe? It may seem surprising, but these tiny and dim stars are everywhere, although they are rarely seen with the naked eye. If we could turn off all the lights in the sky and only leave the red dwarfs lit, the Milky Way would light up like a city at night. However, from our planet, we almost never notice them. Why is this? The key lies in their low luminosity. Although they are numerous, their light is so weak that only a few manage to shyly peek into the human eye without the help of telescopes. Are they distributed randomly, or do they follow some pattern? Red dwarfs do not cluster in special areas of the galaxy. Instead, they are part of the stellar fabric that runs through spiral arms, the halo, and even the central bulge of the Milky Way. In fact, if we take a small imaginary cube of space anywhere in our galaxy, it is very likely to contain several red dwarfs. They are like cosmic dust, invisible from a distance, but omnipresent if one gets close enough. They can be found both in the quiet neighborhoods of interstellar space and in regions where new stars are born. And what happens in other galaxies? The most fascinating thing is that red dwarfs are not exclusive to the Milky Way. In nearby and distant galaxies, astronomers have found clear evidence that red dwarfs dominate the stellar population. Although we cannot see them individually in distant galaxies, their presence is detected by the accumulated brightness and the spectroscopic analysis of the light from those galaxies. Thus, they are a kind of secret ingredient that makes up most of the stars in the observable universe. Is it possible to find a red dwarf near us? Absolutely yes. In fact, the closest star to the Sun, Proxima Centauri, is a red dwarf. In the solar neighborhood, most of the nearest stars belong to this category. If the Sun were replaced by a red dwarf, our night sky would be much darker. Red dwarfs are the invisible neighbor stars, silently surrounding us. And although they go unnoticed, they form the fundamental skeleton of the galaxy, supporting the stellar structure much more than we imagine. When we think of stars, the first thing that usually comes to mind is the Sun. But have you ever wondered how big or small other stars can be in comparison? Red dwarfs, despite being the most abundant stars in the universe, go unnoticed due to their tiny size and modest mass. Are they really as small as they say? The answer is surprising. A typical red dwarf has between 1/10 and half the mass of the Sun. That is, if the Sun were a huge watermelon, a red dwarf would be like an apple, or even a plum. In terms of size, the difference is even more striking. The radius of a red dwarf can be just 1/5 of the solar radius, which means that dozens of them could fit inside the Sun. Can you imagine a star so small, yet capable of shining for trillions of years? That's how red dwarfs are. Although their volume is much smaller, they contain enough mass to maintain active nuclear fusion for incredibly long periods. This efficiency is due to the fact that they utilize almost all of their fuel, unlike larger stars that waste much of their hydrogen. And what if we compare them to other stars? Red dwarfs sit at the lower end of the stellar scale. Blue giants, for example, can have dozens of times the mass of the Sun and a size so enormous that they could engulf the entire solar system. In contrast, red dwarfs are discreet, humble, and compact. But that doesn't make them any less important. In fact, their low mass makes them extremely stable and long-lived, qualities that turn them into perfect natural laboratories for studying long-term stellar evolution. It is intriguing that, although they are small, red dwarfs can have a significant gravitational influence on their nearby planets. A planet orbiting as close to one of these stars as Earth does to the Sun would be much closer to its star due to the low luminosity, yet would still feel an intense gravitational pull. This affects everything from orbital speed to conditions for life. Thus, the size and mass of a red dwarf not only define its appearance, but also the fate of the worlds that surround it. What makes a red dwarf have that peculiar hue against the vast dark backdrop of the cosmos? To understand this, we first need to talk about its temperature. Red dwarfs are cool stars compared to others, with surface temperatures ranging from about 2,500 to 3,500 degrees Celsius. When compared to our Sun, which reaches around 5,500 degrees at its surface, the difference is notable. This low temperature is precisely the main reason for its color. While hotter stars shine in bluish or white tones, red dwarfs emit most of their light in the red and infrared range, hence their name. But why does a star's color depend on its temperature? The answer lies in the basic physics of thermal radiation. When an object is heated, it emits light of different colors depending on its temperature. If you've ever seen a metal rod heat up to a glowing red, you've witnessed this same principle in action. At lower temperatures, objects tend to emit reddish light. At higher temperatures, the light turns white or bluish. This is why red dwarfs, being relatively cool, glow in that characteristic reddish hue, almost like cosmic embers that never quite ignite. And what about brightness? Despite being the most abundant stars in the galaxy, red dwarfs are so dim that they are invisible to the naked eye from Earth. Their low temperature not only determines their color, but also their luminosity. They emit so little light that if a red dwarf were to replace the Sun in our solar system, Earth would be plunged into perpetual twilight, barely illuminated like in the last moments of sunset. Most of the energy they release is in the infrared, a type of light that our eyes cannot see, but specialized telescopes can detect. The temperature and color of red dwarfs also influence their life and the environment surrounding them. Their soft and steady light may seem unimpressive, but it is key to the long-term stability of these stars. Because they burn their fuel at such a slow rate, their temperature remains stable for billions of years. Thus, each red dwarf is like a cosmic low-energy lamp that patiently shines as the universe ages. And although their glow may seem humble, their reddish hue is a silent reminder of the secrets that the cosmos still holds in its dimmest lights. What are red dwarfs really made of? This is a fundamental question for understanding both their behavior and their role in the universe. At first glance, we might think that all stars are similar, but the chemical composition of a red dwarf hides fascinating secrets. The main ingredient is hydrogen, the most abundant element in the cosmos. In fact, more than 3/4 of a red dwarf's mass is hydrogen. This gas is the raw material that fuels nuclear fusion in its core, the process that allows it to shine for billions of years. However, hydrogen is not alone. The second most important element is helium, a product of hydrogen fusion. As the star ages, helium accumulates in the core, but unlike more massive stars, red dwarfs constantly mix their interior due to total convection. This means that helium and hydrogen are efficiently distributed throughout the star, preventing the formation of separate layers. It's as if the interior of a red dwarf were a pot of soup that never stops stirring, ensuring that the ingredients are always well mixed. Are there other elements present in a red dwarf? Yes, but in much smaller amounts. Carbon, oxygen, nitrogen, and other heavier elements are found in tiny proportions, generally less than 2% of the total mass. These elements are referred to as metals in the language of astronomy, even though they are not metals in the common sense. The presence of these metals can vary depending on the region of the galaxy where the star was born as previous generations of stars enrich the interstellar gas with these elements. And why is this composition important? The amount of hydrogen and helium determines how long a red dwarf can live, while the amount of metals influences the formation of planets around it. A star with more metals tends to have a greater chance of forming complex planetary systems. Therefore, knowing the chemistry of a red dwarf not only tells us how the star works, but also whether it can host potentially habitable worlds. In summary, although they seem simple, red dwarfs are cosmic laboratories where chemistry and physics combine to shape the evolution of the universe. How can a red dwarf star be born in the vast and cold space? It all begins in the depths of a giant molecular cloud, a dark and dense region composed mainly of hydrogen and cosmic dust. These clouds may seem tranquil, but chaotic movements occur within. Turbulence, shock waves, and collisions triggered by nearby supernova explosions, or the pressure from other forming stars. What happens when a small part of this cloud, much denser than the rest, begins to collapse under its own gravity? As the material compresses, temperature and pressure rise rapidly in the core of this contracting region. It's as if hundreds of mountains of gas and dust are pushed toward a single point, creating a protostar. In this process, gravity is the great architect, stacking matter layer upon layer, while the internal heat continues to grow. When does it stop being just a cloud and become a star? The crucial moment occurs when the central temperature reaches several million degrees. At that instant, hydrogen begins to fuse into helium, releasing energy and marking the birth of a new star, a red dwarf. But why do some stars become red dwarfs and not luminous giants? The key lies in the amount of available material. Red dwarfs are born in regions where gas accumulation is not so massive. In fact, their final mass will be only a tenth or up to half the mass of our Sun. That difference condemns them to a quiet and long life, but it also limits their luminosity and temperature. It's like comparing a small campfire, which burns slowly and for a long time, to a huge bonfire that consumes its fuel quickly. Interestingly, red dwarfs are the most common type of star in our galaxy. Every time a molecular cloud gives rise to a new generation of stars, most of them end up being red dwarfs. Their formation process, although less spectacular than that of larger stars, is essential to understanding how matter is distributed in the cosmos and how planetary systems form around these small but long-lived stars. Thus, the birth of a red dwarf is a fundamental chapter in the history of stellar life, a reminder that even the humblest beginnings can have a gigantic impact on the universe. What exactly happens in the heart of a red dwarf? The answer lies in one of the most powerful and fascinating forces in the universe: nuclear fusion. Unlike what occurs in larger stars, where fusion can be a chaotic and voracious process, in a red dwarf, it is an act of delicate and efficient balance. Within its core, hydrogen atoms combine to form helium, releasing energy in the process. This phenomenon is similar to a perfectly calibrated combustion engine, where the fuel is used with astonishing slowness and precision. Why is this process so efficient in red dwarfs? The key lies in their low mass and relatively modest temperature compared to other stars. With less mass, the pressure and temperature in their core are lower, causing fusion to occur at a more leisurely pace. Imagine a small campfire that burns slowly throughout the night, instead of a bonfire that consumes all the wood in just a few minutes. This leisurely pace allows red dwarfs to make use of almost all their hydrogen, while in stars like the Sun, much of that hydrogen remains unfused in the outer layers. A fascinating detail is that, in red dwarfs, hydrogen fusion occurs mainly through the proton-proton cycle, a process that requires lower temperatures than other fusion mechanisms. This cycle is less explosive and more stable, contributing to the longevity of these stars. Did you know that red dwarfs can live for trillions of years thanks to this efficiency? No other known star can match that record of duration. The nuclear fusion in them is so slow and stable that so far, no red dwarf has reached the end of its life since the birth of the universe. But what does all this mean for their environment? Nuclear fusion not only keeps the red dwarf shining for eons, but it also determines the amount and type of energy it emits. This energy is what heats its planets and could, in theory, allow for the existence of life. Thus, the process of nuclear fusion in a red dwarf is much more than a simple chemical reaction. It is the silent and constant engine that drives one of the most abundant and long-lived types of stars in the cosmos. What is the secret behind the astonishing longevity of red dwarfs? While many stars like our Sun live for a few billion years before exhausting their fuel, red dwarfs defy the rules of time. Astronomers estimate that these stars can survive for trillions of years, far longer than the current age of the universe itself. But how do they achieve this? The key lies in their modest size and their slow-paced lifestyle. Unlike more massive stars that consume their hydrogen quickly and die in spectacular explosions, red dwarfs burn their fuel slowly and efficiently, like a tiny candle that takes an incredibly long time to extinguish. To understand it better, imagine two cars, one sports car that accelerates at full speed and uses up its gas tank in no time, and another compact car that moves along steadily and efficiently, covering vast distances with the same fuel. Red dwarfs are that efficient car of the cosmos. Their low mass means that the pressure and temperature in their core do not reach extreme values, allowing them to fuse hydrogen at a much slower rate compared to larger stars. This leisurely process grants them an incredibly long lifespan. Did you know that so far, no red dwarf has reached the end of its life since the birth of the universe? This is not just a fun fact, it is direct evidence of how young they are in cosmic terms. All the red dwarfs that exist today are still in their active phase, fusing hydrogen and shining quietly. If the universe were a library, red dwarfs would be the newly placed books on the shelves, patiently waiting to be read for a very, very long time. And what does this longevity imply for the future of the cosmos? When other stars have exhausted their energy and vanished, red dwarfs will continue to illuminate the darkness. Scientists believe they will be the last sources of light before the universe completely goes dark. In other words, red dwarfs are the guardians of stellar eternity, carrying the torch of life and energy when everything else has come to an end. What happens during the life of a red dwarf? Unlike larger and brighter stars, red dwarfs live a remarkably long and quiet life cycle. It all begins within gigantic clouds of gas and dust, where hydrogen gradually concentrates until it forms a protostar. This process, although silent on a human scale, is the first step of an existence that defies imagination due to its duration. Once the red dwarf reaches sufficient mass, nuclear fusion ignites in its core, and the star enters the main stage of its life, the main sequence. Did you know that a red dwarf can remain in the main sequence for trillions of years? To put it into perspective, the Sun will live in that stage for about 10 billion years, but a red dwarf could surpass it by hundreds of times. This is because they consume their fuel extremely efficiently. It's as if you had a candle that burns so slowly that although it is small, it will illuminate for an eternity. This slow pace means that red dwarfs have never been observed dying. In fact, the universe is not old enough for any to have reached the end of its life cycle. But how does the life of a red dwarf end? When they finally exhaust the hydrogen in their core, they do not explode like supernovae, nor transform into spectacular red giants. Instead, fusion gradually shifts to the outer layers, and the star begins to contract and heat up. There is no dramatic ending, but a slow transition. The red dwarf becomes a blue dwarf, a theoretical stage that has yet to be observed before cooling down and slowly fading away as a white dwarf. It is such a slow process that it could exceed the current life of the universe by a long shot. Throughout this time, red dwarfs maintain a surprising stability. They do not undergo abrupt changes or chaotic stages, unlike more massive stars. Their life is, in a way, a cosmic marathon. They move slowly but never stop, defying the rush of the cosmos. That is why the life cycle of a red dwarf is the perfect example of how, in the universe, patience can be the key to survival. While other stars live fast and die young, red dwarfs hold the secret to stellar longevity. Did you know that red dwarfs, despite being small and modest stars, can be surprisingly temperamental? Contrary to what we might imagine, these stars are not calm beacons in the cosmos. Their stellar activity is intense and, at times, unpredictable. But what does it really mean for a star to be active? The answer leads us to discover a world of surprising phenomena, such as stellar flares and changes in brightness that can occur in a matter of minutes. Red dwarfs are famous for their variability. This means that their luminosity can change abruptly and frequently. What causes these dramatic changes? The secret lies in their powerful magnetic fields, much more intense than the sun's in proportion to their size. These fields can twist and release enormous amounts of energy all at once, generating powerful eruptions called stellar flares. Imagine a solar storm multiplied several times. These flares can temporarily increase the star's brightness and eject charged particles at astonishing speeds. But variability in red dwarfs is not limited to explosive flares. Over time, these stars can display activity cycles, similar but much more chaotic than solar cycles. It has been observed that some red dwarfs spend relatively quiet years and suddenly enter periods of intense agitation with multiple eruptions in just a few days. Why does this happen? The key lies in the way these stars transport energy from their core to the surface, which keeps their magnetic fields in constant motion and change. Now, why is the stellar activity of a red dwarf so important? Because it affects not only the star itself, but also everything around it, especially any planets that may orbit nearby. Flares can alter the atmospheres of these planets, and even jeopardize the possibility of life existing on their surfaces. Thus, red dwarfs show us that, although they may appear calm and discreet from afar, within them lie unpredictable forces that keep astronomers and astrobiologists around the world on edge. Did you know that the magnetism of a red dwarf can be thousands of times more intense than that of the Sun? This may sound surprising when we think about its small size, but here physics plays a fascinating role. Red dwarfs spin rapidly when they are young and, thanks to their completely convective internal structure, generate very powerful and complex magnetic fields. But what do we mean when we talk about total convection? It means that the material throughout the star is in constant motion, as if the entire red dwarf were a pot of boiling water. This perpetual movement helps create and maintain intense magnetic fields. And how does this magnetism manifest? One of the most notable effects is stellar flares, gigantic explosions of energy that can release in a matter of minutes as much energy as the Sun does in several days. These flares originate when the magnetic field lines twist and violently reconnect. On Earth, we experience auroras thanks to our planet's magnetic field, but around a red dwarf, things become much more extreme. A planet too close could face true radiation storms, capable of sweeping entire atmospheres away, or profoundly altering conditions for life. But why do red dwarfs maintain this magnetism for so long? Unlike larger stars, their internal convection never stops, and the process of generating magnetic fields remains active even after billions of years. In fact, the intensity of the magnetism often depends on the star's rotation speed. The faster it spins, the stronger its magnetic field. Over time, red dwarfs spin slower, and gradually, their magnetism begins to weaken. However, even in their old age, they can still show significant magnetic activity. The magnetism of red dwarfs not only affects nearby planets, but also influences the star itself. The most active regions can create dark spots on the surface, similar to sunspots, but much larger and longer lasting. Additionally, stellar winds, driven by the magnetic field, carry particles into space, affecting the surrounding environment. In summary, Magnetism is one of the most fascinating and relevant characteristics in the life of a red dwarf, capable of determining the fate of any planet around it and keeping astronomers in constant awe of its incredible power. What makes red dwarfs so different inside compared to stars like the Sun? The answer lies in a fascinating phenomenon: total convection. While the Sun has an internal zone where energy is primarily transported by radiation, and an external zone where convection takes the lead, in a red dwarf, convection absolutely dominates the entire internal structure, from the core to the surface. But why does this happen, and what are the consequences? To understand it, let's think of a pot of soup heating on the stove. The heat at the bottom causes the liquid to rise, while the cooler liquid descends, creating a continuous cycle. Something similar happens inside a red dwarf. The energy created by nuclear fusion in the core does not flow quietly outward. Instead, the layers of hot gases rise and the cooler ones sink, keeping the material of the star in constant motion. This continuous mixing process occurs throughout the star, not just in one zone, making it extraordinary. How does this affect the life and evolution of a red dwarf? Total convection allows fresh hydrogen from the outer layers to be transported to the core, while at the same time, the products of fusion rise to the surface. This means that the red dwarf uses its fuel much more efficiently than stars like the Sun. In other words, it utilizes almost all of its hydrogen throughout its life. If we compare it, it's like a candle burning evenly from the center to the edges, rather than just burning from the wick. Another curiosity arises from this phenomenon. How does convection influence the magnetic activity of these stars? The constant agitation of the material inside contributes to the generation of intense magnetic fields, responsible for powerful flares and variations in brightness. Furthermore, total mixing influences the observable chemical composition on the surface, allowing heavy elements produced in the core to reach the outer layers. Therefore, total convection not only defines the internal structure of red dwarfs, but also determines their behavior, longevity, and even their impact on the planetary systems surrounding them. In summary, total convection is the key that turns red dwarfs into true laboratories of stellar efficiency and magnetic activity. Without this phenomenon, these small stars could not live for billions of years, nor exhibit the variety of physical processes that make them so intriguing for astronomy. The next time you think of a red dwarf, imagine a heart beating relentlessly, mixing and renewing its interior for a cosmic eternity. Did you know that the closest red dwarf to our Sun is also the nearest star to Earth after it? It's called Proxima Centauri. Although its name may sound modest, it holds fascinating secrets. Proxima Centauri is located just over 4 light-years away in the constellation of Centaurus. At that distance, the light it emits takes more than 4 years to reach us, which, on a cosmic scale, is practically being next-door neighbors. Now, what is Proxima Centauri really like? This small star is so dim that it cannot be seen with the naked eye from Earth, despite its proximity. Compared to our Sun, Proxima Centauri has barely 1/8 of its mass and just a little over 12% of its diameter. Imagine a soccer ball next to a marble. That's how different their sizes are. Its surface temperature hovers around 3,000 degrees Celsius, much lower than that of the Sun, giving it that characteristic reddish hue and a luminosity that barely reaches 0.5% of solar brightness. But why is this tiny star so important? It turns out that Proxima Centauri is not alone. At least 2 planets have been discovered around it, one of which, Proxima b, is located in the so-called habitable zone. This has sparked the interest of astronomers and astrobiologists. As if there is liquid water on its surface, it could be a candidate for hosting life. However, the story is not that simple. Proxima Centauri is famous for its intense stellar flares, explosions that can make life on its planets a real challenge. Proxima Centauri is part of a triple star system, along with Alpha Centauri A and Alpha Centauri b, 2 larger and brighter stars that orbit each other, while Proxima remains a distant companion. This stellar trio has been a source of inspiration for science fiction and the human dream of traveling to other worlds. If humans ever managed to reach another star, Proxima Centauri would be the most logical destination, the closest gateway to our cosmic neighborhood. Thus, the nearest red dwarf reminds us of how vast and mysterious the universe is, and how many secrets await to be discovered right next door. How many red dwarfs actually exist in the universe? You might think that, due to their small size and low luminosity, they are a cosmic rarity. However, the reality is exactly the opposite. Red dwarfs are by far the most common type of star in the Milky Way and in most known galaxies. Astronomers estimate that about 7 out of 10 stars in our galaxy are red dwarfs. If we imagine the Milky Way as a city, red dwarfs would be like the humble and discreet houses that, although they hardly attract attention, make up the majority of the stellar neighborhood. What accounts for their astonishing abundance? The answer lies in their longevity and mode of birth. Red dwarfs form from the same clouds of gas and dust that give rise to other stars, but their low mass and slow fuel consumption allow them to exist for billions of years, much longer than larger and brighter stars. It's as if they are the savers of the cosmos. They spend their energy slowly, and that's why, while other stars have already vanished, they continue to shine quietly, accumulating over time. Now, if they are so numerous, why don't they fill the sky with their glow? The trick lies in their low luminosity. Although there are hundreds of billions of red dwarfs just in our galaxy, most are so faint that even the most powerful telescopes cannot detect them all. No red dwarf is visible to the naked eye from Earth. In fact, if we could see all the red dwarfs surrounding us, the night sky would look completely different, sprinkled with millions of tiny reddish points. Studies suggest that, in the observable universe, red dwarfs could outnumber all other classes of stars combined. This means that when we talk about the stellar composition of the universe, we are actually describing a cosmos dominated by the silent yet numerous presence of these small stars. Their ubiquity makes them an essential element for understanding the structure and evolution of galaxies, and it raises a fascinating question. In a universe so filled with red dwarfs, how many unknown worlds are orbiting around them, waiting to be discovered? Did you know that although red dwarfs are the most abundant type of star in the universe, the vast majority of us have never seen one with the naked eye? Why does this astronomical mystery occur? The key lies in their luminosity. Red dwarfs shine with an intensity that, compared to stars like our Sun, is astonishingly low. Imagine a dim light bulb in the middle of a brightly lit stadium. Even if there are thousands of those little lights, their brightness pales in comparison to the more powerful floodlights. This is how red dwarfs are, emitting only a fraction of the light produced by a star like the Sun. But how much less luminous are they really? A red dwarf can be up to 10,000 times less luminous than the Sun. This low brightness doesn't mean they are rare. On the contrary, they account for about 70% of all the stars in the Milky Way. However, their faint glow makes them practically invisible to the naked eye, even if they are relatively close to us in cosmic terms. In fact, most of the stars we can see in the night sky are actually much less numerous, but significantly more luminous. This phenomenon raises an intriguing question. If they are so close and so common, how do we know of their existence? The answer lies in technology and scientific ingenuity. Astronomers use specially sensitive telescopes to detect the infrared light emitted by red dwarfs, as much of their radiation falls within this range that is invisible to the human eye. Additionally, techniques such as parallax analysis and studying how they gravitationally affect their planetary systems allow us to identify and study their properties, despite how hidden they are from the naked eye. The difficulty in observing them has not prevented them from being the subject of enormous scientific interest. Despite their apparent shyness, red dwarfs can host fascinating planetary systems and, due to their longevity, play a crucial role in the evolution of the galaxy. So, The next time you look at a starry sky and wonder how many worlds and stars you are missing, remember that the universe is filled with these little red gems, discreet yet omnipresent, waiting to be discovered with the right tools. Did you know that red dwarfs might be the most common hosts of planets in the universe? Recent research has revealed that these small and long-lived stars often have planetary systems around them. And not only that, they seem to be especially prolific in the formation of rocky planets, similar in size to Earth. Why does this happen? One theory suggests that, forming from less massive gas clouds, red dwarfs generate compact and dense protoplanetary disks, facilitating the accumulation of matter in close orbits. Thus, the planets that form are much closer to their star than, for example, Earth is to the Sun. This proximity implies very different conditions from what we know. A year on a planet orbiting a red dwarf can last only a few days or weeks in Earth time. Additionally, due to the star's low luminosity, the so-called habitable zone, the region where liquid water could exist, is much closer to the red dwarf. Does this make it easier or harder to find habitable worlds? The answer is not straightforward. On one hand, the closeness facilitates the detection of these planets through methods like transits, as they frequently cross in front of their star. On the other hand, that proximity exposes them to intense flares and stellar radiation, which can complicate the existence of stable atmospheres. So, what kind of planets do we find around red dwarfs? Studies have identified a wide variety, from gas giants to super-Earths, and, most interestingly, Earth-sized planets within the habitable zone. One of the most famous examples is the TRAPPIST-1 system, where 7 rocky planets orbit an ultra-cool red dwarf, and at least 3 of them could harbor conditions suitable for liquid water. This discovery has revolutionized the search for life beyond the solar system and has placed red dwarfs at the center of modern astrobiology. However, life on these worlds would not be simple. Many planets orbiting so close to their star may be tidally locked, always showing the same face to the red dwarf, like the Moon does with Earth. This could create thermal extremes, one side perpetually illuminated and the other shrouded in darkness. But science is advancing, and climate models suggest that, with a sufficiently dense atmosphere, heat could be distributed, allowing for habitable zones. Given the vastness of possibilities, red dwarfs and their planetary systems have become one of the most promising and challenging scenarios in the search for life beyond our planet. Where can life exist around a red dwarf? This question has fascinated astronomers for decades. The so-called habitable zone, that ring around a star where liquid water could persist on the surface of a planet, is very different when the host star is a red dwarf. Unlike our Sun, red dwarfs are much less luminous, which means their habitable zone is much closer to the star. If a planet wants to have suitable temperatures for life, it must orbit at a surprisingly small distance, sometimes so close that a complete orbit can take only a few days. But is this really an advantage in the search for life? On one hand, proximity means that planets within the habitable zone receive enough energy to maintain liquid water, the essential ingredient for life as we know it. However, closeness also brings unique challenges. For example, many of these planets may end up gravitationally locked, always showing the same face to the star, just as the Moon does with Earth. What are the consequences of this? One side permanently illuminated and the other shrouded in darkness, creating thermal extremes that challenge climate stability. The habitable zone around a red dwarf is, proportionally, much narrower than that of more massive stars. It's like trying to find the exact point where it's neither too cold nor too hot in a room with a small heater. Small changes in distance can mean the difference between a frozen planet and a scorched one. Additionally, variations in the luminosity of the red dwarf can shift this zone over time, destabilizing conditions for life. Does this mean that life is impossible in these environments? Not necessarily. Theoretical models suggest that if a planet has a dense atmosphere and efficient heat circulation, It could distribute energy evenly and allow habitable zones on the surface, even under extreme conditions. Thus, the habitable zone of a red dwarf is a territory of contrasts and challenges, but also a place where astrobiology finds a fascinating and full of possibilities field of exploration. The key question is not whether there can be life, but what that life would be like under a sun so different from ours. Is it possible for life to exist around a red dwarf? This question has fascinated astronomers and astrobiologists for decades. Red dwarfs are small, long-lived stars, which means their planets have billions of years to develop conditions suitable for life. But is that enough? The debate remains open, as both their advantages and challenges are unique in the known universe. On one hand, the longevity of these stars is a key advantage. While stars like the Sun have a limited lifespan, red dwarfs can shine for trillions of years, providing a stable environment for life to evolve. Imagine a star that watches over its planets like an oil lamp that never goes out. This gives life a much larger window of time than in other stellar systems. Additionally, many red dwarfs have planetary systems with rocky planets located in the so-called habitable zone, where liquid water could exist. However, it's not all that simple. Red dwarfs tend to be unpredictable in their youth, launching powerful flares and radiation that can strip nearby planets of their atmospheres, especially if they lack a strong magnetic field to protect them. This raises a question. Can life arise or survive under such attacks? It's like trying to light a candle in the midst of a thunderstorm. The possibility exists, but the environment is hostile. Furthermore, planets around red dwarfs tend to be so close to their star that they can become gravitationally locked, always showing the same face, which creates temperature extremes. Despite these challenges, the possibility of life is not ruled out. Some scientists suggest that life could take refuge beneath the surface or in oceans, shielded from radiation. Others propose that, with a sufficiently dense atmosphere, a planet could distribute heat and maintain stable conditions. The imagination of astrobiologists goes beyond Earth, considering life forms adapted to extreme environments, capable of surviving where we could barely imagine. In summary, red dwarfs open an intriguing door in the search for life in the universe. Their combination of longevity, abundance, and extreme conditions makes them natural laboratories to explore the limits of habitability. Are we facing the greatest opportunity to find life outside our solar system, or simply a series of insurmountable challenges? For now, the answer remains one of the greatest mysteries of modern astronomy. What challenges do planets orbiting a red dwarf face? At first glance, it may seem that having such a long-lived and stable star would be an advantage for the development of life, but the reality is much more complex. The extreme conditions these worlds are subjected to make existence, as we know it, a true feat. To begin with, the habitable zone of a red dwarf, that is, the range where a planet could host liquid water, is much closer to the star than in the case of our Sun. This means that planets must orbit almost right next to their star, receiving a much more intense amount of radiation and stellar wind. Have you ever wondered what happens to a planet that orbits so close to its Sun? One of the main problems is the so-called tidal locking. In this situation, the planet ends up always showing the same face to the star, like the Moon with the Earth. Thus, one hemisphere remains in an eternal scorching day, while the other is plunged into a perpetual and icy night. This extreme temperature contrast can generate violent winds and gigantic storms in the thin twilight strip that separates both hemispheres, further complicating any possibility of climatic stability. But there's more. Red dwarfs, especially young ones, tend to be much more active than previously thought. Can a planet survive the powerful flares and ultraviolet radiation emissions from its parent star? These eruptions can be so intense that they strip the atmosphere from nearby planets, eliminating any chance of retaining breathable air or liquid water on the surface. Even if the planet manages to maintain an atmosphere, it would be subjected to continuous bombardments, altering its chemical composition and complicating the formation of stable organic molecules. As if that weren't enough, the star's own magnetism and the planet's proximity hinder the existence of a strong and lasting planetary magnetic field, leaving the surface practically defenseless against stellar wind. Without this protection, the atmosphere erodes over time and radiation reaches the surface directly, creating extremely hostile conditions for life. Thus, although red dwarfs are abundant and long-lived stars, the planets that orbit them must face a set of extreme challenges that make life, if it manages to arise, truly exceptional. What would happen if a solar storm was so intense that it could wipe out the atmosphere of an entire planet? Red dwarfs, although they seem calm from afar, are actually the scenes of violent outbursts known as stellar flares. These eruptions release enormous amounts of energy and radiation in a matter of minutes, often exceeding the intensity of the flares emitted by our own sun. But why are they so frequent and powerful in red dwarfs? The key lies in their powerful magnetic field and the dynamics of their interior, which favor the accumulation and sudden release of magnetic energy. The consequences of these flares can be devastating for the planets that orbit close to the star. Unlike solar systems like ours, where the habitable zone is at a safe distance, in red dwarf systems, potentially habitable planets are much closer to their star. This means that every time a flare occurs, these worlds receive a direct and powerful dose of ultraviolet radiation and X-rays. If a planet has an atmosphere, this bombardment can heat it, erode it, and even strip it completely of its essential components, such as water and protective gases. Can life withstand such extreme conditions? Experts debate whether life could adapt, or if stellar flares represent an almost insurmountable barrier. Some scientists imagine that, on these planets, life could take refuge underground or in the oceans, protected from lethal radiation. However, the atmosphere plays a crucial role as a natural shield. If flares are too frequent or intense, they could prevent an atmosphere from remaining stable long enough for life to evolve and thrive. It's like trying to build a sandcastle on the shore while giant waves constantly wash it away. In addition to the direct threat of radiation, flares from red dwarfs can trigger powerful stellar winds, sweeping charged particles at dizzying speeds. These winds increase atmospheric erosion and cause auroras much more intense than those we see on Earth. The result is a hostile and dynamic environment where each flare can change the fate of a planet in a matter of hours. This reality poses enormous challenges for the search for life in red dwarf systems, but it also fuels scientific curiosity. Could there be a planet that has withstood millions of years under this constant bombardment? The answers to these questions could forever change our understanding of life in the cosmos. How is it possible to know the age of a star that is light years away? The answer is surprising. By observing its rotation. Red dwarfs spin on their axes, and that rotation speed acts like the star's internal clock. Just like a top that spins quickly when it's new and gradually slows down over time, a young red dwarf rotates rapidly, while an old one does so much more slowly. In fact, astronomers have learned to measure the pace of that spin to estimate the age of these stars, a method known as gyrochronology. But why does rotation decrease over time? The process is fascinating. A red dwarf, like any other star, has a very active magnetic field, especially during its youth. This magnetic field interacts with the stellar wind, a constant flow of particles that the star expels into space. As the stellar wind carries away some of the star's angular momentum, it gradually slows down its rotation. It's a mechanism similar to a skater extending their arms to reduce their spin speed, but on a cosmic scale. How much can a red dwarf slow down? Unlike more massive stars, red dwarfs can maintain a moderately fast rotation for billions of years, especially the smaller ones. However, over time, almost all of them noticeably slow their spin. There are red dwarfs that, after tens of billions of years, rotate so slowly that their days could last longer than a complete Earth year. This slowdown has direct consequences on their magnetic activity and the occurrence of phenomena like stellar flares. Now, measuring rotation is not as simple as it seems. Red dwarfs are dim and their surfaces are covered with dark spots. Similar to sunspots, that appear and disappear. Astronomers observe the periodic changes in the star's brightness, caused by these spots as they rotate, to calculate how long it takes to complete a full turn. In this way, rotation becomes a key clue to understanding not only the age of the red dwarf, but also its past and future. Thus, each spin of these tiny stars hides the story of their long and unchanging cosmic life. What happens inside a red dwarf over billions of years? Although they appear unchanging from the outside, their internal chemistry is actually in constant transformation. Red dwarfs, like other stars, function as enormous nuclear laboratories where hydrogen fuses to form helium. However, unlike larger stars, these small and tenacious stars make use of almost all their fuel thanks to their total convection processes. This means that the material from their core and surface constantly mixes, as if you were stirring a soup to ensure every spoonful has the same flavor. But what does this constant mixing imply for their chemical evolution? Over billions of years, hydrogen gradually decreases, while helium accumulates inside. However, due to efficient convection, fresh hydrogen from the outer layers always finds its way to the core, allowing fusion to continue for an extraordinarily long time. It's as if a lit candle could renew itself, keeping its flame much longer than seems possible. Over time, the proportion of helium slowly increases. This change in composition slightly alters the efficiency of fusion and consequently the luminosity and temperature of the star. However, these changes are so gradual that, from a human perspective, the red dwarf appears identical over tens of billions of years. Only when it has nearly exhausted all its hydrogen does the next stage of its life begin, although no known red dwarf has yet reached that point due to its practically unmatched longevity. Is it possible that these chemical changes could cause a red dwarf to evolve into something different? Scientists believe that, in the future, when hydrogen runs out, the star could become a blue dwarf, hotter and brighter for a brief period, before slowly cooling down and transforming into a white dwarf. But this is such a distant future that no red dwarf has had enough time to experience it. Thus, red dwarfs offer us a fascinating glimpse into the slow and profound rhythms of stellar evolution, where chemical changes are a delicate and prolonged dance of atoms that will last far longer than the history of our own sun. What happens when a red dwarf reaches the end of its long stellar journey? It's a fascinating question because, unlike more massive stars like the Sun, no red dwarf in the universe has yet reached that final stage. Red dwarfs are so long-lived that, even after more than 13 billion years of cosmic history, none have had enough time to die. However, astronomers have developed theories about their fate, and one of the most intriguing is the possibility that, in their final moments, these stars become what is known as a blue dwarf. How is it possible for such a cool and dim star to end up transforming into a blue dwarf? The answer lies in the physics of nuclear fusion and the internal life of these stars. For most of their existence, a red dwarf fuses hydrogen into helium very efficiently and steadily, extending its life for trillions of years. But as the hydrogen in its core runs out, the star begins to slowly contract. This contraction increases the pressure and temperature in the core, and although the amount of available fuel decreases, the efficiency of fusion temporarily increases. And what happens during this contraction? As the surface temperature rises, the red dwarf begins to emit a bluer light. It's a slow but remarkable process. The star, once dim and reddish, becomes hotter and brighter, migrating in the visible spectrum toward blue. This stage, known as a blue dwarf, is theoretical. Scientists predict it will be very brief compared to the star's long previous life. It is a final burst of energy before the nuclear fuel is completely exhausted. Does this mean we will see blue dwarfs in the sky at some point? The reality is that it won't be soon. It is estimated that these stars will need much more time than the current age of the universe to reach that phase. When it finally happens, the blue dwarf will be a short transition, almost like twilight before nightfall. After this stage, the star will end its life as a white dwarf. a small and dense remnant that, although it no longer produces fusion, will retain heat for trillions of years more, slowly cooling until it loses all its brightness. Thus, the final fate of a red dwarf is a story of extreme patience, of subtle changes, and silent transformations that occur on timescales that challenge human imagination. The hypothesis of the blue dwarf reminds us how vast and mysterious the processes of the cosmos are, and how even the humblest stars can have surprising endings, reserved for a future so distant that even words fail to describe it. What happens when a red dwarf reaches the end of its long journey? Although these stars can live for billions of years, much longer than any other in the known universe, their final destiny is, surprisingly, written from their birth. Unlike more massive stars, which end their lives dramatically in supernova explosions, the end of a red dwarf is much quieter but no less fascinating. As it exhausts its hydrogen fuel, the red dwarf begins a transformation process that, although slow, will lead it to become a white dwarf. Is it possible to imagine a universe so old that there are already dead red dwarfs? The answer is intriguing. We do not yet live in that era. All the red dwarfs that have been born since the beginning of the universe are still shining, as their fuel consumption rate is incredibly efficient. But what will their end be like? When a red dwarf has fused almost all its hydrogen into helium, its core will begin to contract slowly. However, it will never reach the temperature necessary to fuse helium, preventing it from swelling into a red giant, as happens with larger stars. Instead of an explosive end, the red dwarf gradually loses its energy. Its luminosity slowly decreases, like an ember that fades very slowly, until all its matter condenses into an extremely dense and small star, a white dwarf. It is a kind of stellar fossil, the final remnant of what was once an active star. This silent destiny is the result of a balance between gravity, which tries to compress the matter, and the pressure of degenerate electrons, which prevents total collapse. Could a white dwarf form immediately after the death of a red dwarf? In reality, this process is so slow that no one in the current universe has yet witnessed the birth of a white dwarf from a red dwarf. Astronomers estimate that it will take many billions of years, longer than the universe itself has existed. When it finally happens, these white dwarfs will witness an era in which the cosmos will be a dark and cold place, populated only by the remnants of stars that once illuminated the galaxies. Thus, the final destiny of a red dwarf speaks to us not only of the stellar life cycle, but also of the most distant future of the entire universe. Why have red dwarfs captured the imagination of writers, filmmakers, and artists for decades? Although they are humble and dim stars, red dwarfs have left a profound mark on popular culture, becoming silent protagonists in countless science fiction and space adventure stories. Being so abundant and long-lived, they represent both the promise of worlds to discover and the enigma of civilizations hidden in the darkest corners of the cosmos. In literature, red dwarfs often appear as the home of exotic planetary systems, where authors explore scenarios of extraterrestrial life under dim and reddish suns. A classic example is Isaac Asimov's novel, The Naked Sun, where the planets orbiting these stars serve as backdrops for alternative societies and moral dilemmas. What would happen if humanity colonized a world illuminated by an eternal crimson light? This question has inspired generations of creators who see in red dwarfs an opportunity to challenge the limits of imagination. In television and film, red dwarfs have been starting points for interplanetary adventures and cosmic mysteries. The British series Red Dwarf uses the name of these stars to title a science fiction comedy set on a lost spaceship in deep space. Meanwhile, franchises like Star Trek have set episodes in systems dominated by these suns, raising questions about habitability and the future of humanity beyond the traditional solar environment. In these stories, the constant red light of a red dwarf becomes a symbol of the unknown, of hope, and of danger in equal measure. Why are red dwarfs so fascinating in video games and comics? Their mysterious nature and potential to harbor unusual worlds make them the perfect setting for adventures that blend exploration, survival, and discovery. Games like Elite Dangerous or No Man's Sky allow players to visit systems around red dwarfs, facing unique challenges associated with their low luminosity and stellar activity. Even in visual art and music, the idea of a sky bathed in reddish light has inspired works that evoke melancholy, isolation, and awe at the vastness of the universe. Beyond entertainment, red dwarfs have also influenced the way the general public perceives the search for life beyond Earth. Often, popular culture gets ahead of science, imagining advanced civilizations orbiting these stars long before astronomers confirmed the existence of exoplanets around them. Thus, red dwarfs not only illuminate the far reaches of the galaxy, but also the deepest dreams and questions of humanity about its place in the cosmos. Did you know that in recent years, research on red dwarfs has made impressive leaps? Technological advancements have allowed astronomers to detect previously unthinkable details. For example, thanks to space telescopes like Kepler and TESS, it has been discovered that many red dwarfs host complete planetary systems, some with Earth-sized planets in the so-called habitable zone. This has revolutionized the search for life beyond our solar system, as red dwarfs, due to their abundance and longevity, are ideal candidates for hosting planets with conditions suitable for the development of life. What makes these stars so special in recent discoveries? One of the most striking findings is the frequency and intensity of their stellar flares, known as superflares. Recent observations have recorded eruptions thousands of times more intense than those of the Sun, capable of drastically affecting the atmospheres of nearby planets. This raises fascinating questions. Could life survive such cosmic storms? Some studies suggest that although these flares can be devastating, they could also provide the necessary energy to trigger essential chemical reactions for life, like the initial sparks of a campfire in the dark. Furthermore, astronomers have refined techniques to measure the atmospheric composition of exoplanets orbiting nearby red dwarfs. Through spectroscopic analysis, they have detected signs of water vapor, methane, and even gases that could be associated with biological processes. While a definitive signature of life has yet to be found, the mere ability to study atmospheres light years away is a monumental achievement. These investigations allow for comparisons of the diversity of planetary systems and a better understanding of how environments conducive to life might form. Another recent discovery involves the rotation and age of red dwarfs. It has been shown that, unlike other stars, they slow their rotation much more slowly. This phenomenon helps explain their remarkable stability and longevity. Additionally, red dwarfs have been identified that, despite being very old, continue to show intense magnetic activity. This fact challenges traditional models of stellar evolution and suggests that many mysteries remain to be solved in the study of these small but powerful stars. In summary, recent years have witnessed a true revolution in our understanding of red dwarfs. Each new finding not only expands our understanding of how these stars function, but also brings us closer to answering one of humanity's oldest questions. Are we alone in the cosmos? How do we manage to observe and study objects as tiny and faint as red dwarfs, lost among the vastness of the cosmos? The answer lies in the development of increasingly sophisticated astronomical tools. At first glance, our eyes are unable to detect most of these stars, as they emit very little light compared to brighter ones. That's why astronomers have had to resort to telescopes specially designed to capture their weak glow and analyze their properties. Traditional optical telescopes, like those used since Galileo's time, are useful for observing some nearby red dwarfs, but soon become insufficient to capture most of these stars. This is where modern technology comes into play. Space telescopes like Hubble and, more recently, James Webb have revolutionized the observation of red dwarfs by operating outside the Earth's atmosphere, eliminating much of the distortion and absorption that affects starlight. The James Webb in particular is like a giant eye that sees in infrared, right where red dwarfs emit much of their energy. This way, we can discover and study stars that would otherwise be invisible. But how do we know what they are made of, or if they have planets around them? This is where spectroscopy comes in, a technique that breaks down the light from the star into its colors, as if we were passing the light through a prism. By analyzing the dark and bright lines in its spectrum, scientists can identify the elements present in the star's atmosphere, its temperature, and even detect planets passing in front of it, generating tiny dips in brightness. It's like reading the barcode of a star millions of light years away. Furthermore, to study the regions where new red dwarfs are formed, astronomers use radio telescopes and millimeter telescopes, capable of capturing emissions from gas and dust in space. Observatories like ALMA in Chile allow us to see the first steps in the lives of these stars, tracing the interstellar material from which they are born. Each type of telescope and technique contributes a key piece to the puzzle, allowing us to gradually understand these small yet abundant inhabitants of the universe better. Thanks to the combination of these instruments and methods, research on red dwarfs is advancing by leaps and bounds. From the detection of potentially habitable exoplanets to the characterization of their atmospheres and understanding their life cycles, the study of these stars depends on precision and technological innovation. Without these tools, red dwarfs would remain mere invisible dots in the night, hiding the wealth of stories and mysteries that we are just beginning to uncover today. Did you know that, although they may seem humble and discreet, red dwarfs differ enormously from other more well-known stars? What makes them so special compared to red giants, white dwarfs, or even our own sun? The key lies in their size, their life cycle, and the way they manage their energy. While the sun, a G-type spectral star, lives for about 10 billion years, a red dwarf can shine for trillions of years, a timescale that challenges human imagination. Red giants, on the other hand, are stars that have exhausted the hydrogen in their core and have expanded massively, becoming hundreds of times larger than the sun before dying in an explosion or transforming into white dwarfs. Red dwarfs, in contrast, are austere and efficient, burning their fuel incredibly slowly. What would happen if we compared a red dwarf to a white dwarf? Although both names suggest smallness, their nature is completely different. A red dwarf is a living, active star, where nuclear fusion still occurs, while a white dwarf is the stellar corpse left after the death of a star like the sun. If we think of it in terms of a campfire, the red dwarf would be a slowly burning ember, while the white dwarf would be a hot rock that no longer produces fire, only radiating the heat it has left. Moreover, white dwarfs are much denser. A teaspoon of their material would weigh as much as a mountain. And how do they compare to red giants? Red giants are spectacular and luminous, visible from enormous distances in the galaxy. However, their life is brief and tumultuous, like a firework that lights up the sky for just a moment. Red dwarfs, in contrast, are stars that go unnoticed, but their longevity makes them the true protagonists of the galaxy in the long run. It's like comparing a marathon to a 100-meter dash. Red giants run fast and burn all their energy in a short time, while red dwarfs move slowly, but for much, much longer. In terms of brightness, the difference is staggering. A red dwarf can be thousands of times less bright than the sun, while a red giant can easily exceed its brightness by hundreds or thousands of times. However, although red dwarfs are difficult to see with the naked eye, their abundance makes them crucial in the composition of the galaxy. In summary, each type of star contributes uniquely to the story of the cosmos, but red dwarfs, with their quiet and enduring life, end up being the true survivors of the stellar universe. What role do red dwarfs really play in the vast stage of the universe? Although they often go unnoticed, these tiny and dim stars are key pieces in galactic evolution. A large part of the cosmic structure revolves around red dwarfs, functioning as the bricks that support the building of the Milky Way and many other galaxies. If they were removed from the cosmos, the number of stars would drastically decrease, and the chemical composition of the universe would be very different from what we know today. Why are they so important for the evolution of galaxies? Red dwarfs act as true reservoirs of hydrogen, the primordial fuel of stars. Due to their low consumption, they maintain their activity for trillions of years, which means they will continue to shine long after larger stars, like our own Sun, have burned out. Their presence ensures long-term stability in the galaxy, providing light and energy consistently to potential planetary systems over unimaginably long periods. Moreover, red dwarfs contribute to cosmic chemistry in a silent yet powerful way. Although their life pace is slow, over eons, they transform hydrogen into helium, and over time, they can form heavier elements in explosions or advanced stages of stellar evolution. This slow and steady process enriches the interstellar medium, allowing future generations of stars and planets to have a more varied and complex composition. Thus, although they seem humble, red dwarfs are true cosmic alchemists. Could we imagine a universe without red dwarfs? Life, as we know it, would likely be rarer and more fleeting. Being so numerous and long-lived, these stars provide unparalleled opportunities for planet formation and, potentially, the emergence of life in unsuspected places. They are the promise of an extended stellar future, and their abundance ensures that, even as other stars fade away, there will always be small red beacons illuminating the darkness of the cosmos. In this way, red dwarfs are not only silent witnesses to universal history, but also indispensable protagonists of the evolution and fate of the universe. What happens when not one, but two red dwarfs find themselves trapped in a cosmic dance? Binary red dwarfs are systems where two of these small and long-lived stars orbit a common center of mass, spinning around each other as if tied by an invisible gravitational thread. While we often imagine stars as solitary, in reality, a significant fraction of them are part of binary or even multiple systems. In the case of red dwarfs, this configuration opens a fascinating chapter in stellar dynamics. At first glance, we might think that two such modest and discrete stars would hardly impact each other. However, the reality is much more interesting. Did you know that the interaction between binary red dwarfs can influence their evolution and the environment surrounding them? When the stars are close enough, they can exchange material, distort their shapes due to tidal forces, and even synchronize their rotations. It's as if two dancers are so in sync that each movement of one affects the other, creating a unique choreography not seen in solitary stars. These binary systems are particularly intriguing for astronomers because they offer vital clues about the formation of low-mass stars. For example, the distance between the two dwarfs can vary greatly. Some orbit so closely that completing a revolution takes just a few hours, while others may take years. This variety allows for the study of how factors like mass, distance, and gravitational interaction influence stellar life. Additionally, the presence of two stars instead of one complicates the fate of any accompanying planet, as the habitable zone can shift unpredictably or even be completely eliminated if the orbits are too eccentric. But what happens if one of the red dwarfs starts to evolve faster than its companion? In some cases, the material lost by one star can be captured by the other, altering its mass and prolonging its lifespan. This process, known as mass transfer, can trigger unusual phenomena such as eruptions or brightness variations, making these systems natural laboratories for understanding extreme stellar physics. It is not uncommon for astronomers to find binary red dwarfs with unexpected behaviors, challenging traditional theories about the stability and longevity of low-mass stars. In summary, binary red dwarfs not only break the myth of solitary stars, but also represent a true celestial laboratory where gravity, chemistry, and time combine to create unforeseen scenarios. Studying these systems helps us better understand the behavior of the most abundant stars in the universe And who knows, perhaps it also brings us a little closer to answering one of the fundamental questions of astronomy. How does a star really evolve when it is not alone? How fast do red dwarfs travel through the galaxy? Although we often think of stars as fixed points in the sky, in reality, they all move at surprising speeds. Red dwarfs, despite their calm and discreet appearance, are no exception. They move through the Milky Way, following complex orbits, dragged by the galaxy's gravity and affected by encounters with other stars, gas clouds, and even remnants of smaller galaxies that have been absorbed by ours. Some can travel at speeds of tens of kilometers per second, while others exceed 100 kilometers per second relative to the galactic center. Why does the speed vary so much among different red dwarfs? The answer lies in their history and place of origin. Younger red dwarfs tend to move in nearly circular orbits within the galactic disk, like cars orderly circling a track. However, older red dwarfs often show more chaotic and elliptical trajectories, crossing the galactic disk at inclined angles and at higher speeds. This is the result of billions of years of gravitational interactions that have altered their original paths. Some have been ejected into the galactic halo, a much larger and less dense region surrounding the galaxy, while others remain bound to the central bulge. Can red dwarfs escape the Milky Way? Although most are gravitationally bound to the galaxy, there are special cases called hypervelocity stars. These stars can reach such speeds that they overcome the gravitational pull of the Milky Way and escape into intergalactic space. While most known hypervelocity stars are of higher mass, it is believed that red dwarfs can also achieve these extreme speeds, typically as a result of violent interactions, such as a close encounter with the supermassive black hole at the galactic center. How do we know all this? Thanks to missions like Gaia, which measure with unprecedented precision the position and motion of millions of stars, astronomers have been able to create three-dimensional maps of stellar trajectories. They have discovered that red dwarfs, due to their longevity, are living witnesses of the dynamic history of the galaxy. Their movements not only reveal their own past, but also help reconstruct ancient events, such as galactic mergers and gravitational waves that have shaken the structure of the Milky Way. Ultimately, although small and modest, red dwarfs travel tirelessly, crossing the galaxy and carrying with them the memory of the cosmos. What is the relationship between red dwarfs and the age of the universe? To answer this question, we must first remember that the universe is approximately 14 billion years old. Red dwarfs, on the other hand, are incredibly long-lived stars. Astrophysical models suggest they can live for trillions of years, far longer than the universe itself has existed. But here arises a fascinating enigma. To this day, not a single red dwarf has been observed to have completed its life cycle and died. Why is this happening? The key lies in their fuel consumption rate. While stars like the Sun exhaust their hydrogen in just a few billion years, red dwarfs do so slowly and efficiently that none have lived long enough to even approach the end of their life. It's as if the universe were a child and red dwarfs had the lifespan of a millennia-old tree. They simply haven't had time to age. Thus, the fact that there are no dead red dwarfs gives us a unique window into the past and future of the cosmos. And what does this imply for our understanding of the universe? The absence of dead red dwarfs is not just a curiosity, it is a compelling clue about the relative youth of the cosmos compared to the potential longevity of these stars. If we ever detected a red dwarf that had already exhausted its fuel, it would mean that the universe is much older than we believe today. But so far, all the red dwarfs we observe remain active, confirming current calculations about the age of the universe. Moreover, the ultimate fate of these stars remains shrouded in mystery. Astronomers estimate that when red dwarfs finally exhaust their hydrogen, they will undergo a very long transformation before becoming white dwarfs. However, this process is so slow that no star of this type has yet reached that stage. In other words, The red dwarfs that exist today will witness epochs of the universe that we can barely imagine. Will they be the last lights in an aging cosmos? That is one of the great questions that astrophysics still cannot answer. What do worlds like TRAPPIST-1, Proxima b, and LHS 300c have in common? They all orbit red dwarf stars and have captured the imagination of astronomers and space enthusiasts alike. Why are these exoplanets so famous? The answer lies in the combination of relative proximity, intriguing characteristics, and above all, the potential to host conditions suitable for life. Red dwarfs, although small and cool compared to the Sun, provide an ideal setting for the search for exoplanets, and some of the most exciting discoveries in recent decades have emerged precisely around them. TRAPPIST-1 is undoubtedly the most famous system. It is a red dwarf star located about 40 light-years from Earth and surrounded by at least 7 rocky planets. What is truly fascinating is that at least 3 of these planets are in the so-called habitable zone where liquid water could exist. For many scientists, the TRAPPIST-1 system is like a compact version of our own solar system, but in miniature and much more mysterious. Can you imagine 7 Earth-sized planets dancing in orbits so close that, from the surface of one, you could see the others as huge moons in the sky? Proxima Centauri b is another major player. Orbiting the closest star to the Sun, Proxima Centauri, this exoplanet has generated great excitement due to its proximity. It is just over 4 light-years away from us, which, in cosmic terms, is like our next-door neighbor. Proxima b is a rocky world that receives a similar amount of stellar energy as Earth does from the Sun, leading to much speculation about its ability to have oceans and perhaps life. However, the intense activity of its star poses considerable challenges, such as powerful flares that could sweep away the planet's atmosphere. LHS 300c, although less known, is worth mentioning. This exoplanet, which orbits a red dwarf about 35 light-years away, stands out because it is one of the closest potentially habitable worlds discovered in recent years. It is estimated to have a mass and size similar to that of Earth, making it an excellent candidate for future observations with advanced telescopes. Could this be the place where we someday detect signs of life beyond the solar system? The study of these famous exoplanets reminds us of something astonishing. Planetary systems around red dwarfs are much more common than previously thought, and due to their longevity and stability, they could be ideal refuges for life on a cosmic scale. Each of these worlds opens up new questions. What other surprises do red dwarfs hold in their orbits? Will these exoplanets be the first places beyond Earth where we find signs of life? The exploration is just beginning, and the future promises even more astonishing discoveries. What if the fate of the search for life in the universe depended on tiny and discrete stars? Red dwarfs, despite their modest size and faint glow, have become unexpected protagonists in astrobiology. Their importance is such that today, many scientists believe that most of the potentially habitable planets in the galaxy could orbit around them. Why? Because red dwarfs are by far the most abundant stars in the universe. If we imagine the Milky Way as a densely populated city, red dwarfs would be the most common apartments, and each could harbor a world where life could arise. The long life of these stars plays a fundamental role. While stars like the Sun burn quickly and die in a few billion years, red dwarfs can live trillions of years, offering their planets a stable environment for almost unimaginable lengths of time. Wouldn't this be a key advantage for life to evolve and thrive? Furthermore, the habitable zone, that narrow ring around the star where liquid water can exist, is much closer to a red dwarf due to its low luminosity. This means that planets in that zone complete short orbits, making them easier to detect and study from Earth. Thus, red dwarfs have become silent beacons for exoplanet hunters and seekers of extraterrestrial life. However, life near a red dwarf would face no small challenges. These stars, although seemingly calm, can unleash powerful flares that bombard their planets with radiation. Could a planetary atmosphere withstand such onslaughts? Or would life have to adapt in ways completely unknown to us, perhaps beneath the surface, or developing extreme protective mechanisms. Scientists debate whether such conditions would allow for the existence of complex life, or if only very resilient forms could survive in these worlds so close to their reddish sun. Current astrobiology is at a fascinating crossroads. On one hand, the abundance and longevity of red dwarfs make their planets ideal candidates for the search for life. On the other, their extreme environments pose unique challenges. Is it possible that the universe is teeming with life around these humble suns and we simply have not found it yet? Or conversely, will the conditions be so hostile that life around a red dwarf will be a cosmic rarity? The truth is that as technology and research advance, the impact of red dwarfs on our search for life continues to grow, promising surprises and perhaps, one day, the most important discovery in human history. Why, being red dwarfs the most abundant stars in the universe, is it so difficult to detect and study them in detail? The answer lies in their discrete nature. Red dwarfs are like the shyest fireflies in a lit field. They emit very little light, and although they are everywhere, their brightness is so low that, even at short distances in astronomical terms, they can go completely unnoticed. To give you an idea, no red dwarf is visible to the naked eye from Earth, not even the closest ones. Their luminosity can be as little as 1/10 that of the Sun, and even much less. This low brightness makes it a huge challenge to distinguish them from the dark background of the cosmos from our planet. In addition, traditional astronomical observation instruments, such as optical telescopes, are not optimized to capture the faint reddish and infrared light emitted by these stars. It's like trying to hear a whisper amidst the noise of a city. The cosmic background noise and the presence of much brighter stars in the same region of the sky make their identification even more difficult. For this reason, astronomers have had to develop specially sensitive detectors and advanced techniques to separate the faint signal of a red dwarf from the rest of celestial objects. Another significant challenge lies in stellar variability. Some red dwarfs can experience sudden increases in brightness due to flares or magnetic activity, which can confuse scientists and make it seem like they have detected a different object or a completely different variable star. Additionally, their small size and low mass cause them to be easily confused with giant planets or even brown dwarfs from a distance, complicating the precise classification of the observed objects. Finally, detecting planets around red dwarfs is even more complicated. Although the proximity of the habitable zone to the star facilitates some methods, intense stellar activity can mask or distort the signals that astronomers are looking for. It's like searching for a needle in a haystack while the haystack is moving. For all these reasons, despite being the main characters of the universe, red dwarfs remain, in many ways, stars in the shadows, constantly challenging the ingenuity and technology of those who wish to unveil their secrets. What is the smallest red dwarf we know of? Surprisingly, there is a star called EBLM J055557AB, whose mass is barely above the threshold needed to be a star. If it were a little lighter, it wouldn't even be able to undergo nuclear fusion and would be a giant planet. Its size is so small that if we placed it next to Saturn, it wouldn't look much larger. This demonstrates that, in the universe, size does not always determine importance. Even the tiniest stars can shine for trillions of years. Have you ever wondered what the most common star in our galaxy is? Red dwarfs earn that title unchallenged. It is estimated that more than 3/4 of all stars in the Milky Way belong to this category. However, despite their astonishing abundance, none are visible to the naked eye from Earth. It's like having a party with millions of people in a dark room. They're there, but no one sees them without a proper flashlight. Their low luminosity makes them invisible to the human eye, even though they dominate the stellar population of the cosmos. Did you know that the life of a red dwarf can last longer than the current age of the universe? Estimates suggest that some could exist for over 10 trillion years, which is more than 700 times the current age of our Sun. In fact, no red dwarf has died since the birth of the universe, making them true records of cosmic longevity. They are the true stellar marathon runners, slowly advancing over unimaginable eras. Another fascinating curiosity is that, due to their completely convective internal structure, red dwarfs manage to utilize almost all of their hydrogen as fuel. This gives them an efficiency that no other star can match. Additionally, some red dwarfs exhibit intense flares capable of releasing in seconds the energy that our Sun emits in days. These eruptions can affect nearby planets, putting any possibility of life to the test. Despite their calm appearance, red dwarfs can surprise with episodes of extreme violence. Finally, what records do they offer us in terms of exoplanets? Red dwarfs are the hosts of some of the most intriguing planetary systems known, such as TRAPPIST-1, which houses 7 Earth-sized planets, all potentially rocky. The proximity of these planets to their parent star means that a year lasts just a few Earth days. Thus, these small stars become natural laboratories for studying strange worlds and perhaps discovering the first hint of life beyond our solar system. What does the future hold for the study of red dwarfs? This question drives the astronomical community to develop new technologies and bold missions. Upcoming space telescopes, such as the James Webb and the European Extremely Large Telescope, are designed to unravel the most hidden secrets of these tiny stars. Will they finally be able to detect atmospheres on exoplanets orbiting them and analyze if they contain traces of water or even chemical signals of life? This is one of the great goals of modern astrophysics, because red dwarfs, though modest, may hold the key to answering the eternal question: are we alone in the universe? Another line of research aims to better understand the magnetic activity of red dwarfs. How do their powerful flares affect nearby planets? To this end, networks of automatic observatories are being developed on the ground and in space, capable of monitoring thousands of these stars simultaneously, recording every flash and every variation in brightness in real time. The data collected will not only help predict the space weather around these stars, but will also be crucial for assessing the habitability of their worlds. The search for exoplanets around red dwarfs will also accelerate thanks to new missions like Plato or Ariel from the European Space Agency. These missions will not only look for Earth-sized planets, but will also attempt to characterize their atmospheres, composition, and orbits with unprecedented precision. Is there a blue planet spinning in the habitable zone of a quiet red dwarf, waiting to be discovered? With each technological advance, the possibility of finding a world where life has flourished under conditions very different from those of our Sun increases. Finally, the future of research on red dwarfs is closely linked to international collaboration and the use of artificial intelligence. Astronomers are developing algorithms capable of analyzing millions of data points in seconds, identifying patterns impossible for the human eye to see. Thus, science is moving towards a new era where uncovering the secrets of these small and common stars could revolutionize our understanding of the cosmos and our own place within it. What mystery do red dwarfs hold? Those small lights that dominate the galaxy, but remain invisible to our eyes without the help of technology. Although individually they are dim and modest, these stars represent the vast majority in the universe, as if the cosmos were filled with tiny fireflies that together form a symphony of energy and time. Their apparent weakness is, in fact, their greatest strength. They live billions of years, far surpassing the longevity of stars like the Sun. Is it possible to imagine an existence so long that no red dwarf has died since the birth of the universe? That's how resilient they are. But why study these tiny stars? Red dwarfs are true cosmic laboratories. Their slow and efficient life cycle allows us to glimpse the fundamental processes of stellar physics and the chemistry of the universe. Moreover, their ability to host planetary systems has transformed our perspective on the search for life beyond Earth. If most potentially habitable planets orbit red dwarfs, could life be more widespread than we imagine, waiting on warm and dim worlds under the reddish light of these silent suns? Red dwarfs also challenge us to think in extremes. How do planets survive their stellar flares? What will happen when the universe ages and only these stars remain as solitary beacons in the darkness? It's as if each red dwarf were a cosmic clock, measuring the passage of time at almost eternal rhythms. Their study reveals secrets about the evolution of galaxies, the fate of matter, and the incredible possibilities of astrobiology. In the end, red dwarfs teach us a fundamental lesson. In the universe, greatness does not always depend on size or brightness. Often, the silent protagonists hold the most fascinating enigmas and the longest stories. Understanding these stars brings us a little closer to the heart of the cosmos, to its deep past and its even more distant future. Who knows what other secrets await to be discovered under the dim red light that dominates the vastness of space?